plate contain magnets. For example, Levitron, there's their toy you see. The top may levitate above the magnetic plate. Under what condition can one observe the phenomenon? Well, here is the video of the phenomenon, and I can show it to you in a live version. Well, here you can see it, but well, I have shaken hands, and well, here you can see it. It was started just in a perfect way. No, it's as I'm starting now. Well, well, for half stability position, we have our object to be stable at all degree of freedoms. We have vertical oscillations, so it should be stable at vertical. Also, we have horizontal oscillation. Oscillations horizontal plane. We can calculate it as 1 degree of freedom because it's all has a vertical symmetry against vertical x. And also we have turning of spinner's x, and turning of our spinner when it's turn out and fall. It also can be 2 degrees, but because it's have symmetry against vertical x, it's 1 degree. So let's sum up. There should exist a force which is equal to 8. Move the spinner to axis of symmetry, prevents turning of the spinner's axis of symmetry. Well, we have this box and we don't know what is there inside. We suggest it could be magnets. So here is a simple magnet, simple ring magnets. In literature, is used to calculate it as a circle current. For each part of a wire with current works Biot-Savart law. Using it, we can calculate magnetic field in any point of the space. And that's how we're going to paint, just not to miss the direction of our current. Well, let's go to the first levitation condition. Force of magnet interaction on vertical force must be equal to weight. Well, here is simple 2 repulsing magnets. As we see, when we turn out the x, it turns round and falling. Let's look at the example at this phenomenon closer. Here is the forces attracted our spinner, which is the top currents. We have difference in forces in horizontal plane, and this causes motion of our spinner from axis of symmetry. And also the difference in vertical plane and causes the turning of our levitron. There is another levitation condition come from the conclusion made from previous one. The levitron must move to the central to the axis of symmetry of our plate. So for this we should have some magnet force which move it to the center. Here is 2 simple attracting magnets, and you can see the phenomena of stabilization in the center. So we make the same vertical cut and look at the forces. And look, really, differences in horizontal plane causes the motion of the spinner to the axis of symmetry. And well, there is also a difference in forces in vertical plane, and it causes rotation, but in other direction. Well, maybe it should compensate another one. Well, we should combine 2 magnets, attractive one and deflective. But how? Well, we decided to cheat, and we measured force against vertical force against vertical x on our experimental setup. We just fixed our spinner to prevent turning and moving from the axis of symmetry, and move the vertical force. So here is this experiment points, and here is our resulting force. It means magnetic force plus mass, plus weight of the spinner. And here is our model fitting. To make our model, we calculated the field in each point of the space, and well, try and integrate on the spinner. Well, here is the result of our approximation. Our upper magnet current is 33 amperes, and radius is about 1.5 centimeters. For down deflective magnet, we have a really big current. It's 857 amperes, and radius for about 4 and 5 centimeters. And the magnet which attracts and stabilizes is, as we see, as not so strong. It's about 26 amperes, and radius about 1.5 centimeters either. Well, we should check some zone of levitation. For this, to make this, we should know how big deflection it can take in horizontal plane. So we decided that our model is rather reliable. As you saw in the experiments, the errors was not very big. So here this force attracts their spinner, and here is it may affect just another way. So here is the plot got from our model, and you can see that on the really not a very small distance we have zone of horizontal stability. And now in this zone of horizontal stability, we can make this plot, as you see on the slide, which is in space. And well, we should turn out the zone of vertical stability, where our force of magnet interaction is more than weight. As you see, well, but as you see, if we just start the spinner, I can later show it you experimentally, it is still falling. Well, we should add some mass. There was some masses in the complex with our toy. So the zone will be smaller, but the stability will be higher. Because when our mass is very small, spinner tries to accelerate on the whole range of stability, and then flies out from the axis of symmetry. Here is the real zone of levitation. Well, I'm sorry. Well, on this video we're shown that the spinner put it in the zone of stability, here for example, just turned round. Well, that's why we should know what turns the spinner. Certainly it's magnetic force, it's moment of magnetic force. Here is plot taken from our model, and well, we know that increasing angle we increase moment of acting force. So we should make something to prevent it. Well, here is a usual spinner. It has some angular velocity, and because it has angular moment of inertia and angular velocity, it has angular momentum. Let's imagine that at some distance a, acting some force F, which causes certainly the moment of force M, which can be calculated by this equation. This is the vector. So it causes some turning of the spinner. But at the same time, the moment of this force is equal to angular velocity of precession multiplied by angular momentum. And as you see from the last equation, that the angular momentum, the angular velocity of precession will be perpendicular to angular momentum. So it would just make precession in such the top of the spinner will make such a movement, and it wouldn't turn around. But well, this is the direction. Well, it was the theory with approximation that our omega, our angular velocity along spinner axis is much more than angular velocity which perpendicular to spinner's axis. But if we wouldn't include this approximation, we will maybe get the condition for stability. Here we should write full angular momentum, and also we should know that first derivative by the time from angular momentum is moment of force. Well, we should take a unit vector on spinner's axis, which shows their top of the spinner. And for this unit vector, we can express angular perpendicular velocity from this vector, as you see on the slide. And from this we can get such an equation, which is main equation for spinners without close approximation. Well, and after some transformation, well, we should put in that second derivative from unit vector s is omega of precession minus omega of precession squared multiplied by r, which is shown on the slide, and also another formula for the first derivative. It's too long. Well, and in final, we will have a square equation against angular velocity of precession. And well, after solving the square equation, we will get something under square root. Well, and if this something will be lower than 0, that means that our physical position is unstable. So this is the condition of stability is that angular momentum squared is more than the shown moment of force multiplied by moment of inertia with some coefficients. And after putting in a moment of force, terribly sorry. Yes, after putting in a moment of force, we can make a plot angular velocity against deflection. And experimentally we have checked just capturing upside the levitron on the high-speed cam that our experimental was a bit bigger. That happens so because our spinner goes far from the real vertical x at the zone of stability, and acting forces are just different. There should be bigger determining forces. So let's go to conclusions. Magnetic field of plate should cause force to compensate weight of the spinner and move levitating magnet to the center. Field of plate can be modeled as a field of two current circles. This model gives us ability to calculate the system by one simple measurement, just making measurement of force in vertical x, and after this we can get everything we need in our model. Magnetic fields cause these forces which turn around the spinner. Rotation of the spinner prevents turning around, as we said. Increasing of angular momentum increases the spinner stability. We can get critical angular velocity from accurate series of gyroscopes and from experiments movies. And as we see in experiment, they will be bigger because our case is not ideal. Well, and also we have some parameters of spinner. The spinner should certainly have magnet, and it should have optimal moment of inertia to have their bigger angular momentum to be given from our hands, and optimal ratio between mass and current in the magnets to get in the best zone of stability. So that's all. Thank you for your attention.
Thank you. Now the opponent has 2 minutes for questions to the reporter.
Okay, can begin with, do you really think that the repulsion force must be equal to weight?
Well, as we said in our measurement, we have some zone when it's equal or bigger, and this zone should be levitation.
Okay, but you see that the spinner is oscillating.
Yes,
vertically,
okay.
Right?
Let me show you the plot.
So, but let me ask you,
Okay.
don't you see that it comes back down after some time? It gets velocity upwards then downwards. So you see that the weight is greater than the force applied. Do you agree with that?
Well, okay, our force depends on coordinate, and our weight doesn't depend on coordinate. And when our spinner goes up, the force of magnet interaction decreases. And that's why force goes by mass starts being bigger. So if we're just didn't make ideal start up, our spinner just started to oscillate. And if the start up was ideal, it will stand in balanced location.
Okay. It's really that circulating current in permanent magnets always a perfect circular motion of
Well, you
electrons.
mean there can we approximate the magnets with the circle currents? Or
But are these approximation real?
well, it's really close to real. We can estimate their induction on the surface of our magnet during to this approximation. Well, we did it, but I don't remember. It's, as far as I remember, 0.5 Tesla for the spinner, and I don't exactly remember for the plasma.
This stability zone that you plot for us is the same for any rotation frequency.
Well, what do you say?
You have a stability plot, right?
Something this one.
In space. That's the same for any frequency, like for higher frequencies.
Well, it don't
for
depend on frequency. Frequency just
Really?
go this slowing down of the spinner. And if
Okay,
we have some
but for
Okay, sorry, that's time up now. So the opponent has 3 minutes for preparing the opposition.
Do we need Limon? You need Limon? I need you to take out your application.
That's right. It's better make you sleep with your laptop, because without difficulties.
Sorry?
The Windows frame. The Windows. The operation system frame.
Reporter, you can choose to stay there until you are asked questions. So you have, now, are you ready to start? Yes?
Yeah.
You will have 5 minutes on your own if you like. If you don't use all of that, you will have 15 minutes altogether with discussions.
15 minutes.
Altogether from
Yeah.
now.
Okay. My name is Lucas. I'm from Brazil and I'm going to be the opponent this time. Okay. Beginning with our analysis over the presentation, we are going to study the experimental setups, drawbacks, and main points, theoretical basis, mathematical model, presentation as a whole, and that's it. Okay, about the experimental setup. They tried a demonstration on site that was a good point. They could show us some videos, but we can actually see that they could not construct their own base. For example, they used already built one. They just analyzed one model. There were many parameters that weren't analyzed, such as the temperature of the spinners that could increase or decrease the magnetic forces, the drag forces generated by the airflows there were not explored. We see too that they could actually explain to us the precession effect, but they could not say to us why the spinner must be spinning altogether, and they could not show us how could they measure like millinewtons forces, like which instrument did they use for that? We don't know. So for some other points, we should talk about together.
You want to start the discussion?
Yeah, we can start the discussion.
Go ahead.
Okay. Again, if I may use the. Okay, you actually said that the force must be equal to weight.
Well, it's certainly equal or more than weight.
But yeah, okay, but let me see that. Have a spinner here.
Yes.
I will represent by this ball. And okay, it oscillates like this, right?
Yes.
Okay, and this is a stable motion, right?
Yes.
Okay, but then you don't see that it gains velocity upwards to like the median, I don't know. To some point it gains velocity, have positive acceleration.
Yes.
Okay, but then it has a negative acceleration here.
Yes.
So it stops on the top. So
Yes.
don't you see that the weight force is greater than the magnetic
Well,
motion?
Can you put me in? Yes.
Okay.
You remember our plot of force on distance.
Okay.
It has some P here. And
Okay.
here is their mass, its weight.
Okay.
And well, at this point it is stable. Because you see, when it goes down, the force increases and it tries to accelerate up. And if it goes up, the force decreases, and that's why it starts oscillation. And in fact, we leave our...
Okay, but at what point should the weight be equal to the force? I
Well,
don't
and-
see that.
well, this is the point where...
Okay,
force-
we have these 2 points, right?
2 points. And
we could
this
plot
point
a-
is unstable, you see?
Okay.
When we decrease our distance, our levitation
Okay.
tries to fall. And when
Okay.
it increases upper. And well, I can show you it's just right now.
Okay, but could you plot for me like the forces applied to the spinner over time for a stable motion, like it would be like this, I don't know, over time of oscillation.
Well,
That would be forces. Could you plot it for me?
forces,
The weight and
forces
the,
from time. Well, it's,
yeah, okay.
well, okay, forces from time. We can
Like
just
this,
well, from this to this, we have oscillation from this coordinates.
Okay, but could
Okay,
you show me?
it will be, for example, a sinus oscillations. So a force also should be the sinus. Something will be like this. Well, it's just an anchor. See?
What would be each one? Have
Well,
a variable weight
it's
here.
positive, it's negative.
A
We have
variable weight.
changing. No, we have changing of force of magnet force. As you see, it's not
What are
constant
these
in
two curves?
coordinate. Well,
these two
okay.
shapes.
Let's go. We have x against time, coordinate
No,
against time.
in this case, force over time, how could you do that?
It's well.
Could you show it
Our
for me?
force is magnet.
No, could
force
you
of,
plot for me, please?
force of time.
Yeah, force
It will
over
be
time,
some
the weight
oscillations.
and the magnetic forces. Could you show it for me,
Well,
please?
separately.
Here, in the same plot. Indicate
Okay.
for me the
Here
weight
is, well,
and
if waist directed down, so it's negative. Okay.
Okay.
And the force is also is positive, and it will be some F1, and
Okay.
here would be some also F1, and here would be such an oscillations
Okay,
over
but
this F1, because our coordinate without ideal starting is changing, so our
Okay.
force is also changing.
okay, could you plot the absolute value of this force here, please? The absolute value.
Our mass was
No, here, please. The
Well.
absolute value would be here, here, or here.
it this one.
Okay, but don't you see that the weight can be higher than the
As
variable
far-
force?
Well, if our spinner is
But
higher
do
than
you agree
balance,
with that?
yes,
This
it can
is
be
greater
higher,
than
of
here.
course.
So we are getting contradiction because you said that the weight force should be always lower.
I should.
Yeah,
and
or
there-
equal.
No. You didn't understand my formulation. I said that in some zone we should have certain zone where force of magnetic
Okay,
attraction
but
is
here,
more than
here
equal.
it is stable and the weight is greater than the magnetic force. Don't
Well,
you agree?
it's stable over this point at some coordinates, from these coordinates
Okay,
to
okay.
this coordinate.
Okay, let's
And
change
then it
topics.
goes out from there.
Okay, there is any limitation for the frequency?
Well,
Is there a higher limit for frequencies?
Well, as a frequency we have only air drag, which stops our spinning. And
Okay,
well,
in vacuum,
in vacuum,
theoretically.
theoretically in vacuum shouldn't be any mechanical frictions, but well, there could be caused some phenomena by magnetic interaction and oscillations. There, if we have ferromagnetic and changed magnet fields, there could be some phenomenon. Then it will be that some energy of oscillations
Okay,
will
okay.
go into
But
magnetic.
would be a higher limit? Simply.
What higher limit?
Would there be a up limit for the frequency?
Any limit for the frequency?
Yeah,
Well,
yes or no?
In fact, it shouldn't be, but it depends on what size.
Yes or no?
Okay, it's yes. If it's infinitive, we can't start our oscillations.
Okay, considering the air drag, did you could you measure any lower limits or higher limits for the frequencies?
For the frequencies of oscillations,
Yeah.
well, we measured lowest frequency for spinning of our levitron. It was 35 radian per second, and well,
Yeah, the lower limit.
and the lower limit, and then it starts falling.
Yeah, that's the lower limit. What about the upper limit?
Well, I don't know what can be upper limit. It can be such a high angular velocity that their angular momentum of our spinner
Okay.
would be so high that we
Could
couldn't
you
even
measure
move
that?
it.
Could you measure that?
I think we couldn't measure that because it's some really great downward.
Okay. It's okay. How did you measure forces actually? You had like millinewton plots and I
Well,
don't know
it
how
was
to do that.
we'll just spring very
You
well
attach it
spring
as spring.
easy to move, and then we
Okay.
add to this spring some weights and small weights and thought, oh, this deflection is accurate same to this force, and then we attach our spinner to the spring through their
Okay.
stick and fixed it to
So
avoid
you-
moving in such moving and
Okay.
such, and
So-
just move it up and down. And
Okay,
by
so
their-
you attach it like a dynamometer to
yes,
the
like
spinner.
a dynamometer, but well, we meant it itself, and it's more accurate because
Like
real
with a
dynamometers.
spring.
with
Don't
a
you
spring.
think that it would like disturb the problem, like having something attached to the to a spinner that would be levitating?
You mean that there
Wouldn't like the degree of freedom like that made the spinner oscillate horizontally be like nullified by that?
we tried to measure the force on the vertical axis.
Okay, but don't you think that
And
would change
of
the
course,
problem?
if we have some deflection, our forces changes. I said it about at the moment when we're speaking about when it's turning around and the critical angular velocity.
Okay, but couldn't you get some other, or think about now of other kind of measurement that would not annoy the experiment?
Well,
by this
what
way?
do you mean annoy?
Just measuring the force without getting any limitation to the oscillation.
We can do limitation for oscillation by adding small masses. But these measurements will be on very small range because our levitron will go out from the balance location. It will be more accurate on the, it's 10 times maybe, but really I don't think that they are necessary because it will be very small range and no theory will fit it.
You said you added a spring, right?
Yes.
But a spring that could be like
Ferromagnetic?
no, a spring that could be like get longer with like millinewtons of force applied.
Well, we took a special spring that which could be easily deflected with low masses, and we measured.
Okay, that's right. Okay, you have the spinner, right?
Yeah.
And then you approximate that to a circular motion that generates the magnetic forces, right?
Well, what do you mean circular motion?
Circular current.
Yes.
That generates the.
It's just a model. It's in fact, in our spinner is ferromagnetic, which have domains which are charged which have certain structure and call this magnetic field. So this current is just a mathematical approximation.
Okay. Did you try to disrupt these domains that will generate actually the magnetic forces, like reaching the Curie point?
How we could do this?
Like just hitting the spinner.
Well, if we hit the spinner, we will kill our spinner effect.
But that would be experiment.
Well, it's experiment, but it's killing experiment. We can make some experiments without killing levitron.
Oh, well, okay. If you had to construct a levitron from this sketch, how would you do it?
Well, in fact, we tried to construct a levitron. I may try to show it to you. Well, if I have time to turn on the projector.
How would that be?
Well,
from the sketch.
Well, in fact, it can be two ferromagnetics. One is big circle, another is small circle.
Why circular?
Well, they are better to replace between each other. In fact,
What would be better?
Well, they have a central symmetry, and the best central symmetry is, of course, have circles. But in our experiments, we tried to make it from a lot of wire taken in the circle. So to try to make, but our coils were too big, and they couldn't be approximated by the simple round circle. Current circle. They had just some height, and that's why they causes some strain in field.
It was lacking, so that it
it wasn't lacking the real stability. Because it was some levitation. There was some done when it was centralized, and some done when it was then the mass was the force of vertical interaction was enough to compensate mass. But these zones didn't come to one point. Well, in the lowest part it was centralized, and here is.
But what would you need for it to work actually?
Well, in fact, if we could make just one current circle and a great current, we will get such a phenomenon. But in real life, it's a problem because all circles are heated. All current.
Okay, so you are saying that the magnet that you have there is like this, right? Have magnets here. That's circular. That's a prism, actually.
But it's
like a prism.
What do you mean prism?
Like
shape.
A prism shape. Prism.
Well, and how could be the prism shape? I don't get it.
Okay, that's a circular magnet, right?
Well, yes.
You have a circular magnet here, right?
Well, in spinner exactly, and
okay, in this spinner.
Yes, in spinner, circle magnet.
Okay, but do you think that it will generate the same magnetic forces as a coil in which would be current. The same.
Well, it will be in very small distance. We will see some differences because while calculations we should divide by numbers which are really very close to zero, and mathematical models can't give us their
Okay,
correct results.
it would be the same or not?
It should be the same. Well, it should be
Should be
very
the same.
very close. Very close.
Very, very close.
Yes.
Okay, but how much weight would you add for this spinner in each experiment? Like 1 gram, 2 grams, like what?
As far as I remember, their weight of their the masses was from 1 gram. Oh, the maximum was about 2 grams, and the lowest was 0.1 gram.
0.1 grams. Isn't that close to zero too?
Yes, it's close
As
to zero,
this is
but
close to this?
but we
Your
have
point
a
of
very
view?
small zone because total mass of our spinner is 20
Okay,
grams.
but if you have a stable motion, then you add this mass. You
Yes.
could be that. Could it be that the stable movement does not happen anymore, right? You could do that.
Yes, we could do this. We could
Okay,
take such a point.
But that's just a little additional mass.
Okay, let me show
Right?
it to you.
So then you
By
have a
fault.
just little difference here. So wouldn't that make you not able to do the spinner actually?
To do the spinner.
This, as you said, that this is just a little different from that. It's
Well,
just a
yes,
little
it
different
gives
from zero.
us some error, but well, we can
Like-
rely on our model.
Like it's 10 to the power of minus 4 to multiply by 10. So it's just a millinewton more here.
That's the last question. That's the last question. You can answer.
So that is just 1 millinewton. So
Well,
if you change by 1
yes,
millinewton
our
you know
model
that-
gives us certain error, and we have certain error in experiments. And well, if we add in 0.1 gram, we couldn't exactly say from the model how it will affect. But
Okay.
if
Thank you very
changing that in is normal range, 2 grams, 0.5 grams, it will be okay.
Thank you very
calculated by
much.
the model.
Thank you. So, I'll ask the reviewer now to ask questions to the reporter and opponent.
I guess the first question.
Can you please
will
stand
be-
up so we can hear you?
The first question would be to opponent. You mentioned in your monologue about other models that haven't been investigated. What do you think one can change in the model?
Okay, so one could actually measure these forces, like just getting the spinner over a precision scale, for example. Then you would measure the contact forces between the base spinner,
I see. Thanks.
and
But
then
what
you will
about
not disrupt.
other models? You said about other.
Okay,
You meant other shape maybe.
Okay. You have a theorem that states that static magnets would not be in stable configurations. And then what would happen is that the precession movement and the stability that comes from that would allow the spinner to be levitating over
I see.
the table. So that would be.
I guess then the next question would be to the both of competitors. So the first to reporter. What do you think? Is there some resistance to the spinning of levitron? And what about some kind of lifetime?
Well, lifetime, it's caused by friction. Well, all resistant force is air drag. And well, if we change the viscosity of our air somehow, the lifetime will be lower. We didn't took out the lifetime of the spinner because we just wanted to find the zone. And because lifetime is, can be changed by their starting process. If we start it very high, it will be longer.
So there are only air drag force.
Well, as I said, there could
Okay.
be some phenomena connected with oscillations of two ferromagnets in field of each other.
And what would you do?
You think that there would be dissipations too, even if you had vacuum, so it will come to a stop or stop.
So it would eventually stop due to what?
It would like drop from the stability zone.
Why? Before there would be no zone, or?
Okay, what happens is that would dissipate energy, like in the oscillation movement.
So at energy you'll be finding those
Yeah.
things. What about your camera when you were shooting the angular velocity?
Well, our cam has had frames per 420 frames per second.
420. So frames. Is there any video that can prove?
You mean the cam velocity?
I mean, no, I don't think. And the last question, I think that I will go over. Why do you think your live demonstration has failed?
Well, live demonstration was failed because I'm a bit nervous and my hands is shaking. I can't start the levitron in an accurate way.
And
Now I
the main
count
point
down,
is to
I can come there and start
maybe,
indicating.
maybe in your finish. Do you think that the problem is solved?
In what way?
Solved within
We
within
couldn't,
its formulation.
we couldn't see like upper limits or lower limits for frequencies. We didn't see like, for example, the configuration of the table if it's.
Let me
Okay, sorry, that's the end of the time that you have. Now you can prepare your review for 2 minutes. Yes. Now have 4 minutes for your review.
So it's already going, yeah?
Can you turn down the light, please? Thank you.
Greetings, good evening. I think I was representing the team of Russia and reviewing the problem number 12, levitating spin. So I think I'll start with a quick overview of the main advantages and disadvantages of the report, and with some remarks to opponent. Well, the demonstration was unsuccessful. I guess it's a little mistake here. It's disadvantage actually. So there was no real demonstration, and opponent has pointed to it. And there were wonderful visual aids in the presentation itself, and its advantage? Rep-Opp-Rev-JQ has performed a sequential and complete research. However, I should point to some negative sides. That there was really a lack of something new. So it seems like the theory that was already worked, already investigated, and we think it's a real negative, it's a real disadvantage of the work that he didn't constructed anything by himself. So as we can see, it's a bought model of Levitating, and here during construction of the experiment, maybe it's the most important part, because one can understand the very matters of each parameters by changing it. Well, as an example, I can say I can put the configuration of magnets inside the base. So as we know, it may be different, and the Levitron would still be working. And it was nothing said about it. Well, we've also seen experimental plots, but however, though despite it was shot by a high-speed camera, it's almost unbelievable that there are no errors on such speed as 24 radians per second. Well, and opponent has also pointed to a disadvantage that forces measurements weren't mentioned, but it was solved during the discussion. I would like to say a few words about it. The discussion was really helpful to the total understanding of the problem. So the main notes, I think, the main points, the reason of spinning, why should it spin? So they worked it out, and opponent has also cleared out how did reporter measured small forces such as millinewtons. Well, and then it was a very important point that about a current direction inside the magnet, and about a model approximation. Well, but I can but point to a few missed points which we think it would be better to discuss. I mean, shape of magnets, maybe aerodynamic and configuration. Lifetime of model, it wasn't investigated.
Sorry,
and,
the time out.
okay, thanks. My last word, problem is solved, but only within this statement of trouble. So the lack of construction is the main.
Okay, that was outside the program. Thank you. Now, the reporter has
Okay, I want to correct a few of my mistakes. I calm down a bit now.
Thanks a lot.
You can come down.
It's already well. We should fix mass at any place we live because we have different magnetic force of the earth, and it could also affect the phenomenon. But we should observe it now.
You have 2 minutes.
Okay.
Полторы минуты.
Oh, he's not listening to me today. So, well, what about the work of the opponent and reviewer? During the position, I really liked the points when he was asking me about making my own experimental model, and I answered that I used to make some coils, but well, he didn't let me to show it. It's a pity, but I think that's okay. I also liked that he tried to propose some other mathematical models, but he didn't say what exactly when the reviewer asked. So, but I didn't like during the discussion that there was paid too much attention at the point how I measured force, because it was, well, I think it was rather clear. And about their plot, which could be explained by one simple plot: force against distance. Opponent tried to say about oscillations of their levitron. I liked the reviewer. That he tried to say about something about accuracy, but we have 420 frames per second, and our frequency is 4 hertz. We can make enough points to make it clearly. Also I liked for him to give mark to the opponent. I think they do their best. Thank you for opposition and review.
Okay, thank you very much. Now it's time for jury members. We have 5 minutes to ask questions to anyone. Yes?
I'd like to ask the reporter, you said you somehow fixed one turn to move only in this direction.
Yes, I can show it on the slide.
I would like to see.
Nice. There was here this slide. As you see, we used a tube to and attach some vertical X, just a usual thin stick. Now, in the mass of the stick, we can measure the force acting on the levitron, and you see it's fixed by the stick and the glass tube. We didn't attach ferromagnetics close to the platform because it certainly will cause a great error for our experiments.
So the levitron wasn't spinning, it was just...
It's tried to spin, but it was fixed in these directions.
So it spinned...
We have a tube, vertical tube. It's fixed really good. Then we put in some stick and fix to the stick the levitron, in a good way. And so it can't move because it's stopped by the tube. It can move only in vertical direction.
So the levitron is inside the tube?
No. There is this tube and the stick is inside the tube, and the levitron is attached downside.
Sorry, can I answer? Because yes, it was just a stick attached to a levitron, and it was placed into the tube. It wasn't spinning around its axis. It was just a small frame measurement of the force. It wasn't any kind of levitation this moment.
So it wasn't spinning, it was just put there?
Yes.
Yes.
Okay, that's it. Thank you.
Is that made possible by the tournament rules to other?
One other in the team can make comments on a question.
But answering.
Well, that's a comment to this answer that we already had.
So
Okay? Yes?
The non-uniformity of magnitude in z direction, how can change the stable point?
I don't catch
The
you.
non-uniformity of the magnitude in z direction, how can change the stable point? I mean, do you measure the uniformity of magnitude in z direction?
What do you mean? Forks? These vertical forks or horizontal?
If you consider one in a loop, or
If we consider, when we make such measurements, we always take an ideal point when our spinner is just in the x of symmetry of our setup. And if it has some deflection, the forces has another, just a bit another value. So it's this measurement is good only for central, and they approximately can say something about the space around it. But it's as you see, our levitron just oscillate at the height we measured, the height.
Okay. Are you happy? Yes. Sorry. Here.
Would you please explain the principal conservation of angular momentum?
conservation of angular momentum.
Conservation, yes, conservation of angular momentum.
Well, okay, we have some spinning thing. For example, these things that makes me cooler. If we try to pick some x in such direction and try to turn it, we will feel some resistive force. But in fact, this force doesn't exist. We just have to pay a big force to change the angular momentum. And well, in fact, that is how in a levitron. And if we try to add some constant force and fix one of the points of the spinner, it starts, the precession will start. Because there, as you see, the angular velocity caused by the moment of force will be just perpendicular to the moment of force. And it wouldn't try to turn around.
No.
I want to ask, did you somehow take into account that the levitron isn't just a point near the
Well, levitron wasn't a point. Levitron wasn't a circle. Well, in model, of course. And the circle is, well, it says us a lot more than a point. And well, it's their estimation we could make for their simple magnet.
Okay, thank you. That's up. Time's up for jury questions. So, I ask the jury now to look into your papers and get them ready.
Please turn on.
Turn on the lights here, please.